Je voudrais remercier Jean-François Colliac là, qui a pris l'initiative de contacter l'AAVSO. Et l'AAVSO a répondu positivement et j'ai le plaisir donc d'introduire David COWALL. David, are you ready? I don't know if you are speaking French, but I'm introduce you in French. So David COWALL est le vice-président de l'AAVSO. Et ça va être une très bonne transition à la fois pour terminer cette session là sur les transits d'exoplanètes et puis préparer la réunion de demain qui va être dédiée donc au binaire à éclipse et comment on peut déposer des observations sur le site de l'AAVSO. So David, it's a pleasure to welcome you in our school, photometric school. It's the second event we organized this year after 2 long years of delay due to the COVID. And so it's a pleasure for me to introduce you, and we are waiting for the last output from AAVSO.
Well, thank you all, and welcome from the AAVSO. My last course in French was in 1967 when I was a university undergraduate, so I hope you will allow me to speak in English. What I wanted to do was to, first of all, my background, I'm a physician, so my expertise is in human biology, not astronomy. But I have been a member of AAVSO for over 25 years, and I'm currently a vice president. So I think I can give you some perspective on the citizen science aspect, and would like to talk about some of the things that we do at AAVSO in terms of photometry, both visual and digital. And what I'd like to cover in the next 30 minutes is to tell you a little bit about our organization, to talk a little bit about our visual observing program, and then to go into our digital observing programs. And this is kind of an evolution that I've gone through as well. And finally, to look at some fairly complex science that our citizen scientists and myself that I was involved with as well have accomplished. The mission of the AAVSO is to enable anyone, anywhere to participate in scientific discovery through variable star astronomy. And so we want to make the tent as large as possible. And we want to encourage citizen scientists from a whole variety of backgrounds to participate. The AAVSO was founded, the American Association of Variable Star Observers was founded in 1911. It came out of the Harvard Observatory, and our first annual meeting in 1911, you can see in the black and white photo, and front and center here is Henrietta Leavitt, as you all recognize in terms of figuring out just the universe is a whole lot bigger than we used to think it was. And this was our annual meeting, I think 2 years ago at the Lowell Observatory in Flagstaff, Arizona. We currently have between 1,000 and 1,500 members from all over the world. We have many professional astronomers, as well as a large amateur membership as well. One of the things that we offer is a rather extensive educational program. There is a wonderful textbook called Variable Star Astronomy, which is intended to be a undergraduate course for non-science majors at university. It's free from our website. We have a whole series of choice courses, which are 4-week online courses from a wide variety of subjects. They are a very modest cost, and we certainly encourage everyone that is interested to actually join. It doesn't cost much to become a member of AAVSO, and you get big discounts on the choice courses as well. And we also have webinars and how-to hours that are offered every month that are free online as well. So a good place to start for a citizen scientist is to learn a little bit about what's going on, and these resources, I think, are wonderful places to start. The visual photometry program is the oldest part of AAVSO. It often doesn't get a whole lot of credit in the professional arena, but certainly for many stars, it's the only variable star data that is available, and it is a great place for people to get started in variable star astronomy. And the place I recommend people start is with binoculars. Most people have a pair lying around the house. If you don't, for a cost of under $100 US, you can buy yourself a nice pair. I recommend lightweight 8x35s. And the great place to start is with Delta Cephei. It is very easy to find, very easy to measure visually. If you can find the Big Dipper and Polaris, you can find Delta Cephei. It is the constellation the King, and right next to it is Cassiopeia, the constellation of the Queen. And what we're interested here, you have to have a little bit of imagination looking at any constellation, but you're looking for the left bicep of the King. And so you stare straight at that star, you bring the binoculars up to your eye, and you're going to see this triangle with Delta Cephei and two comparison stars, Zeta and Epsilon. You can see the star varies from magnitude 3.5 to 4.4. And it's a simple matter of interpolating your apparent, how you see the brightness of the target versus the two comp stars. If you're not familiar with looking at some of our star charts, the number of the star is its magnitude to the nearest tenth with the decimal point eliminated, so we don't confuse the decimal point with another star. And so I would read this at right about 3.5, 3.6. Once you've practiced a little bit, most people can get within a tenth of a magnitude pretty reliably. There are a number of other Cepheid variables whose periods are about a week that are also easy to find and are quite bright. So you can easily develop a little repertoire for each of the seasons and get practice visually looking at variable stars. Delta Cephei has a period of a little over 5 days, characteristic sawtooth light curve where it goes up rapidly and then dims gradually. And having such a short period, you get a bit of instant gratification. You know, a month or two of observations, you can layer one light curve on top of another, get a nice phase plot out, and get a sense of what's going on in the star with just your own observations. You want to invest a little more and get a little more sophisticated. Well, you need to get a telescope. My suggestion for a starter telescope is a 6 or 8 inch Dobsonian. These are well under 500, and if you're a do-it-yourselfer with a piece of sonotube and some mirrors, you can make one yourself. And the star I recommend starting with is our Leo. It is by far the easiest to find. The constellation Leo, which actually looks a bit like a lion, is easy to find in the southern sky in the spring. This backwards question mark at its base is the prominent navigational star Regulus, very easy to find in a small telescope. And you just drift the image slightly to the right and you come to our Leo. This is an M star, it's a Mira variable. So it's a pulsating variable of a period of about a year. I think it lists here at 310 days. It is about the mass of our sun. It's what our sun is going to do in a few billion years. And the star is very prominently red, so it's no mistaking it for the other stars in the field. Through our website, you can print up a star chart of whatever field of view that you want, and you can orient it however you want to match your telescope. Reflecting telescopes, you get inverted images, so you can make it south up as shown here. And again, you just pick the comp stars that are a little brighter, a little dimmer, and can come up with magnitude measurements. So these are great places for young people. This is great projects for particularly high school students to get started in photometry. But most of photometry these days is digital, CCD or CMOS. But there you're talking about a lot of technical expertise, and you're talking about a lot of expense. And so one of the things we offer is the AAVSO net. And this is a network of telescopes, both in the northern and southern hemisphere. They are 100 to 200 millimeters in aperture. So these are small aperture scopes. So we're looking at the near sky. As a benefit of membership, members can request proposals to look at various stars or sequences of stars. And so it's an opportunity to participate in pretty sophisticated CCD and CMOS photometry without any personal expense. Now, many of our members do have their own equipment, and some of them have extremely elaborate equipment. But this is, as I said, this is an opportunity for anyone, anywhere to participate. Now, my particular part of this project was setting up and maintaining the Texas instrument. So if you look on the map at the top of the page, you see an arrow, and it points to where I live in Maryland, on the east coast of the United States. But I was frustrated with the sloppy weather and high humidity on the east coast of the United States, and wanted to put the telescope in a more useful location and to link it with the AAVSO net. So in terms of a little bit of American geography, the state of Texas, its border with Mexico is the Rio Grande River, which you can see here. And the map on the lower left here is a light pollution map of that area. So at the very western tip of Texas is El Paso and its sister city Juarez in Mexico. And you can see the terrible light pollution in that area. And to the northeast is Midland and Odessa, Texas. And you can see their signatures of light pollution. But kind of in the middle there, up in the Davis Mountains of West Texas, is the darkest skies in North America. And literally, when the moon is down and it's cloudy, which isn't very often. It's so dark you can't see your hand in front of your face. So it's a perfect location for an observatory. And so have leased space in the dark sky observatory, which is located on a mountaintop about 1,850 meters of elevation. It is bone dry, and it has the other two things you need for a remote observatory. It has electricity and it has broadband internet. And here you can see these are roll-off roof observatories. There's 11 pier in each of them. There's actually one more that's been built since I went out there for the first time. So there's 11 in each. So there's 33 piers here, which are rented by commercial companies, the government, and private observers as well. Our instrument here is seen at the southern end of this instrument. So we're facing south here. And this is a closer view of the Bright Star Monitor, Texas. And the instrument is a 100 millimeter refracting telescope on a German equatorial mount with a CCD camera. It yields 2 arc seconds of resolution and has a field of view of 2.5 degrees. So this is a nice wide field of view and pretty decent resolution. What you can see on the bulkhead here is a web power switch, so we can, through the internet, turn on and off the power to each of the different systems. And the one piece of hardware you can't see is the onboard computer, which is bolted to the backside of this pier. So basically, the way this remote robotic system works is, in addition to the computer, and the computer, by the way, since my name is Dave, I had to name it Hal. I just couldn't resist that. And there are 3 pieces of other hardware. There's the optical tube assembly, there's the camera, and then there's the mount. The optical tube is driven by focusing software. The camera is driven by imaging software, and the mount is driven by navigational software. And then we use executive software, which controls all the other software programs. And so it actually has a fair amount of built-in artificial intelligence. Every clear evening, once the roof rolls off, it powers up and it takes a set of dusk flats. It then does its observing run for the night and shuts down. And periodically, about every 3 months, as the temperature changes, we reset the temperature for the camera cooler and use the cloudy night to do a full set of dark and bias frames. And once the onboard computer goes into its observing run, it looks at the list of targets. It sees how well positioned they are going to be in that particular night sky, how much of a nuisance the moon is going to be. And it goes through the list and it decides which is the best. It does the observing run on that star, and then it starts this cycle over and over again. And so 2,000 miles away in Maryland, I am dialing into the onboard computer, and this is what my desktop looks like. We have Focus Max, which is the focusing software. The run starts with a focus run, and every few hours during the night, it will touch up the focus. Depending on the results, we may want to do a slight offset to improve our photometry. The navigational software, unfortunately, is covered up by other windows, but it's SkyX. The camera software is Maxim DL. And then our executive software is ACP. And here we have the scheduler, and this scheduler has a list of all the possible targets. And what we've done is we prioritize the targets. And then the lowest priority, we have a survey list of under-observed variable stars. And so if there is extra observing time, we don't want the scope to sit idle. And so it will default to these survey stars if we've run through all our priority list. One of your participants today, Dr. Lequec, does have a proposal with us for an exoplanet. An exoplanet run does require us to do a time series, and that does tie up a telescope for several hours. So we can't do that all the time, but we do have a number of 3 to 5 hour time series. You know, a project of mine that I'm going to tell you about in a little bit, you know, involved a time series as well. And we have to look at, as you saw in our chart, we have we have observatories on the east and west coast of the United States. We have one in Hawaii, which is in the tropics, but is still northern hemisphere. And then we have one on the east and west coast of Australia. Australia actually has kind of a nice weather pattern in that usually if one coast is clouded over, the other coast is clear. So it's pretty likely that if it's a southern target or way southern target, and we're using the Australia instruments, we're going to get data from one of the two of those instruments. So the project I've been interested in, and to give you a little idea of some of the science that can be done, is BW-VOL. This is a beta Cephei star. It is a monster. It is about 14, 15 times the mass of the sun. And it is a pulsator as well, with a period of about 0.2 days, so about 5 hours. And I did some preliminary work on this star and presented a little abstract at one of our annual meetings, and was contacted by Dr. Odell, who's had retired from Northern Arizona University, but was working at the Lowell Observatory, and he was very interested in the star as well, and so wanted to partner with me. Unfortunately, in the midst of our project, he passed away, but we continued the study. This is shows you a single image from our Texas observatory, and all of our data from people that issue proposals goes into our cloud-based software program called VFO. So it's free software through the cloud to any member, and you submit a proposal, then all your data is downloaded into VFO. Now, you can see BW-VOL with the green bullseye around it. We have 2 comp stars with the blue bullseyes around them, and then 1 check or quality control star. And so this is ensemble photometry. Unfortunately, BW-VOL, because it's so massive and because of its physics, most of its energy is from UV. So it's hard to get good comp stars that are good matches in magnitude and color. You like a lot more than 2, but this is the best we can get. And the software then does an analysis, and you can see here this particular measurement was a magnitude of 6.800. Our check star is well within range of its published magnitude as well. So this particular image we were pretty comfortable with. And here's a representative light curve in both V and B filters. And since most of the energy is in UV, you get a little better picture of the light curve with a B filter, and you can see there's a little bit of a characteristic still stand that you're not seeing with the V filter. And you can see the 95% confidence intervals. So with our small instrument, we're getting, I think, very good photometry. So how do we think about doing the science on a star like this? And our director, Stella Kafka, is Greek, so I felt I had to have one slide about the Greeks. And so there's two ways to think about thinking. And science is, you know, whether it's medicine or astronomy, is about critical thinking. And you can think rationally like Plato, or you can think empirically like Aristotle. And you can see Plato here is pointing up because it's all about the mind and how we rationalize and reason in our minds the solution to the problem. Aristotle, on the other hand, has his hand out. He says, oh, no. We need to look at the physical universe. We need to look at the data, and we need to let the data speak. It's our observation that's important. And so the most critical way to think about a scientific problem is how to play off the rational versus the empiric. It's not a zero-sum game. And so what we do in medicine, astronomy, and many other disciplines is we look at the observed and the calculated together. And we look at an O-C or a residuals analysis, which is what we did for BW-Vol. And keeping it simple, if we plot these residuals over time and the results are linear, then we conclude that the star's period is staying the same. If we see a change and a new straight line develops and the slope of that straight line is negative, then we see that the period is decreasing. And again, relative to the previous straight line, if we see a new path where a new straight line where the slope is increasing, we see that the period is increasing. And if we look at the history of BW-Vol, it tends to follow a pattern of a constant period, which you see in these blue lines, for about 10 years. And then we see a new line with a positive slope compared to the previous line. And this seems to happen about every 10 years. And a model of that is this orange plot, which is very parabolic. However, based on that model, somewhere around 2004, we should have seen an increase in the period, but you can see this straight line continued to about 2009, 2010. So if we take our data from AAVSO and we compare it and we add it to the data from the Lowell Observatory, this is that last data set from 1982 to 2004. And this is our data combined from AAVSO and from the Lowell Observatory. And it's interesting that there were a few occasions where we actually observed the same time series of the star, and the data was absolutely congruent. It was spot on between the two instruments. So in terms of accuracy, we felt very confident about our data. But what we are seeing here is instead of seeing around 2004, the expected period increase and a new line sloping upward, we see a downsloping line with a decreased period. So what is this telling us about the star? Well, anything you would put in a publication would be rejected by the referees because you would be speculating. What we're seeing, what this tells us is the empiric, what happened. It doesn't tells us the what, it doesn't tell us the why. But since this is not being published other than being recorded, I can speculate along with my co-authors. And what we're probably seeing is a change in the convection currents inside the star. But we obviously don't know that. There are a lot more, the star needs to continue to be observed. And the star being so massive, it's likely going to end in a kaboom. And are these changes reflective of the star getting ready to supernova? You know, we just don't know. So that gives you a little bit of a survey of what the AAVSO is and what our observing programs have been, and just one piece of science that we've done. I can't begin to cover all of the aspects of the organization. But I wanted to stop there. First time I went out to West Texas to get the observatory set up, I flew into El Paso and rented a car. And as I turned off the interstate and headed into the Davis Mountains, it was early spring, and the cacti and the bluebonnets were all in bloom. I had to stop and get off and contemplate the vastness of it all. And so I'd like to end with this slide and open up to any questions.
Thank you very much, David. It was very nice to hear you and to have this presentation, particularly on your last variable stars. It's very fascinating that such a stable star, in fact, is not, and there is science behind. Okay, maybe some question, or and keep in mind that yes, tomorrow morning we will have a special session on binary stars.
All right, thank you all very much for inviting me.
Thank you, Dave. I have a question for you. Can amateurs like us do the monitoring of your star, or how does it work?
Absolutely.
Do you need it?
We have an international database, the AID, AAVSO International Database, and we certainly encourage all of our members, all of our observers to post their data on the database. It can all be done through the website. Once that data is in the website, then that data is available to our analysis software like Avvso, and also we have another cloud-based software program called vStar, which can do a lot of the more hairy math. And I would point out that the math that I had to do to figure out the timings of the maxima was easily enough done just using Excel spreadsheet. But a lot of the other analyses, you really need a much more powerful engine. So the vStar is just wonderful for that. It does great calculations of mathematical models and a whole lot of other things as well. So we get the data in the AID, and then you can go from there. And we'd love to have you submit data on BWVol.
We hope so with my students. Thank you, Dave.
Thank you.
Okay, thank you very much, Dave.